Hello friends, in this video we are going to see the numerical on VCR where the temperature limits are given and the cooling capacity is given in indirect means. Okay, so we'll see the statement. So here is the statement given: the vapor compression refrigeration system using R12 as the refrigerant. So they have given the refrigerant as R12, which is working between -25C and 40C. So this is the evaporator pressure. Lowest will be the evaporator definitely, and the 40 will be that is the highest will be the condenser. So evaporator and condenser temperatures respectively. The vapor is superheated by 5 degree, okay, before entering to the compressor, and the liquid is subcooled by 5 degree. Okay, so there is the superheating before entering to the compressor and subcooling by 5 degree after the condensation. Okay, use pH chart, and we are supposed to find out COP in mass of refrigerant per TR, piston displacement per TR, heat rejected, and the COP. Fine. I'll draw the pH diagram over here for understanding. Okay, so fine. So this is the, let's say, temperature lines we are drawing first. Draw the temperature line. This is -25 and this is, let's say, 40 degree. Fine. So what they have given, that the point number 1 ideally for standard VCR it will be on the saturation curve. However, they have given there is a superheating of vapor by 5 degree. So if the evaporator pressure is -25 and if I am having the superheating of 5 degree, so the temperature at the exit of evaporator will be -25 plus 5. Okay, so evaporator temperature, that is temperature at point number 1, will be evaporator temperature plus the 5 degree plus 5 degree, that is the degree of superheat given. So here it is -25 plus 5, I will be getting the -20 line over here. So somewhere over here we'll have the -20 line, this is -20, and then we'll have the curve of -20. Wherever both these lines are intersecting, that is, we know that the superheating, this is the degree of superheat. Okay, this is, let's say, the point number 1 dash, this is 1 dash, and this is the 1. So 1 dash to 1 is the degree of superheat, and this superheating will be at the constant pressure. Fine, this will be at the constant pressure. So wherever it is intersecting the evaporator pressure line and the -20 degree Celsius line, this is -20 degree Celsius line, wherever it is intersecting, I will get the point number 1. Now from here, the isentropic process will follow up to the next temperature line, that is the 40 degree condenser temperature line. Fine. Then after condenser process, basically there is the subcooling by 5 degree. Okay, so the condenser temperature is 40 degrees. So obviously if there is the subcooling, the temperature at the exit of condenser, that is the point number 3 temperature, will be condenser temperature minus the degree of subcooling, that is 5 degrees. So it is 40 minus 5, you will have 35 degrees Celsius. So we'll be having, this is, let's say, the 40 degrees Celsius line. Okay, somewhere over here we'll have the 35 degrees Celsius line. Somewhere over here we'll have the 35 degrees Celsius line, something like this. Okay, so here, okay, I'll just draw like this. So this up to the 35, this is 35 degrees Celsius. Up to 35 degrees Celsius, the subcooling will be done, or the condensation will be done. Again, as you know, the subcooling, that is from 3 dash to 3, this particular process will be at the constant temperature. Always remember this superheating process and subcooling process, both the processes are taking place at the constant pressure only. So I'll be having the condenser exit point will be the point number 3 over here at 35 degrees Celsius, and then we'll follow the constant enthalpy line up to the evaporator temperature. I'll get the point number 4. So this is how the entire cycle will complete. Okay, I'll just dark this cycle. So 1 to 2 compression, 2 to 3 condensation, 3 to 4 expansion. Fine. So now what we will do, we will go to the chart and we'll plot the points first of all. Okay, fine. Okay, now as they are given, the evaporator temperature is of -20. So fine, this is the, oh yeah, first you see the chart, this is the R12 chart. So -25 they are given. So this is the line of -25. This is the line of -25 degrees Celsius. Okay, mark this first. with respect to that there will be some pressure. Okay. Now as you know that there is a superheating by 5 degrees Celsius, so the exit of evaporator will be having temperature of -20. So this is the -20 line up to this, and then it follows the curve over here. So this line, wherever it is intersecting to this particular pressure line, evaporator pressure line, you get the point number 1 over here. This is the point number 1. This is the point number 1. Okay. Now the next is the temperature of condenser is given. So what is the temperature of condenser? That is 40 degree. Fine. So this is the 40 degree Celsius temperature line. I'll just follow with respect to this particular temperature. There will be the pressure line. So that pressure line I am just continuing further, because we know that the superheating and the subcooling will be at the constant temperature only. Constant pressure only. So from this particular point number 1, I need to follow the isentropic line up to this particular pressure line. So these are the isentropic lines. I'll follow the parallel line to this isentropic line, something like this. Okay, somewhere over here it will intersect. That point is nothing but the point number 2. That point is the point number 2. Now from point number 2, there is the condensation will be starting, and the condensation will end at point number 3. But the point number 3 is after subcooling, and the subcooling is up to a 35 degrees Celsius temperature, because the subcooling is given as 5 degrees. So 40 degrees the condenser temperature, and less 5 degrees subcooling, that is 40 minus 5 will have the 35. So if you observe, this is 30 degrees, this is 40 degree. So somewhere here in between we'll have the 35 degrees Celsius line. We'll have the 35 degrees Celsius line. So wherever the line of this 40 degrees Celsius temperature or the pressure is intersecting with the 35, you'll get the point number 3. You'll get the point number 3. And from here you'll follow the straight line over here down, which will give you the point number 4, wherever it is intersecting to the evaporator pressure, evaporator temperature, which is of -25. Then this is 40 degrees Celsius. This is 1 to 2 process, compression. 2 to 3 is condensation. Okay. So whenever the superheating and subcooling is given, please take care that both the process takes place at the constant pressure only. You just have to add or subtract the degree of superheat and the degree of subcooling respectively from the evaporator and condenser temperatures. Fine. So this is what the point number 1, 2, 3, 4. With respect to point number 1, we'll just find out the enthalpy over here. So this is about 340. We'll have the enthalpy of H1. I am noting down the enthalpies over here. So that enthalpy for H1, that is the a compressor inlet is 340 kilojoule per kg Kelvin. It is 3 kilojoule per kg. Then we'll have the enthalpy at point number 2 over here. This is the point number 2. And point number 2, you'll have the enthalpy somewhere over here. You just follow the straight line from point number 2, wherever it is coming down. Now I don't have the scale over here, I'm just drawing roughly. It is between 350 and 400, so around 375. Sorry, I just mark it this point number 2, or enthalpy is 375 at point number 2. Then we'll find the enthalpy at point number 3 over here. That is this enthalpy. Now follow this particular straight line over here again. Okay, now it is again falling down somewhere over here, 200, 225, 250, around 230, let's say. So H3 is equal to H4. We know that the process is isenthalpy. So that is 2, how much we say? 35. You can note it, 235 maybe. Fine. So you have got all the enthalpies H1, H2, H3 and H4. We'll just go by one by one. So first bit was the COP. So only when they are asking the COP, it is nothing but the theoretical COP, and the formula to get the theoretical COP is H1 minus H4 upon H2 minus H1. Okay. So put the all values of H1, H2, H3, H4. You will get the answer of COP as 3.69 around. Okay. You just note it. Okay. Just calculate that, because whatever answer I have got, I just written, and these values are again what you can see the judgment values I have taken. I don't have the scale over here. Then the second one, they are asking the mass flow rate. They are asking the mass flow rate of a refrigerant per TR. Mass of refrigerant per TR. Now fine, the mass of refrigerant MR is how much? So to get the mass of refrigerant, I need to have the cooling capacity. So here the cooling capacity or the heat absorbed, or what you can say the refrigerating effect formula, is equal to MR into H1 minus H4, that we know, H1 minus H4. So if I know this particular refrigerating effect or the heat absorbed or the cooling capacity, then easily I can get the mass of refrigerant, because H1, H4 I have values with me. However, in this particular statement, if you read very carefully, there are nothing mentioned about the refrigerating effect over here or the cooling capacity over here in the statement. But if you go by the beats over here, they are clearly mentioning that the mass of refrigerant per TR, it is per TR. So what is that is given, that you consider the cooling capacity is a 1 TR, and with respect to 1 TR what the mass of refrigerant is, that you are supposed to find out. So here in this case, in my case, the refrigerating effect is nothing but the 1 TR. So that 1 TR I am converting to kilojoule per minute by multiplying it by 210, okay, into MR into H1 minus H4. You get the answer of MR. Okay, that answer may be around 0.03 kg per second. What I have got the answer, you just again cross verify those answers. Okay, so here the important thing is that mass of refrigerant, whenever you are supposed to get, you see what is the cooling capacity. If the cooling capacity is not directly given, read the statements carefully to get the cooling capacity. Now the third bit is the piston displacement per TR, where volumetric efficiency is 0.83. Now we know the piston displacement formula, which is nothing but MR into specific volume divided by volumetric efficiency. Now here this particular V1 value, that is a specific volume, I can get it from the density, because I know that on the chart I do not get directly the specific volume, but I get the this particular density, and from the density I can get the specific volume. So with respect to the point number 1, if I go by this particular density line, I'll just mark a parallel line to this density line. It is around 7.5. So I'll be having the rho 1 as 7.5 kg per meter cube. Just take the reciprocal of this. I'll get the V1 value, which is nothing but 1 by rho 1 by 7.5. Okay, you will get the V1. Volumetric efficiency they have given as 0.83. MR you have calculated over here, and from that you can get the piston displacement. Okay, the one thing is, if you are putting this particular MR in kg per second, the piston displacement will be in meter cube per second. What I suggest you put always this value of MR in kg per minute. While calculating the piston displacement, so that you can get the piston displacement in meter cube per minute. Okay, so the piston displacement what I have got is around 0.3 meter cube per minute. 0.3 meter cube per minute. Again I am requesting you, please verify your answers with the correct values. Then the point number 4, the bit number 4 is what? Heat rejected in the condenser. Yes. Now what is the condensation process? Condensation process is from 2 to 3. Okay, so heat rejected in the condenser will be the difference of these 2 points, H2 minus H3, but the answer will be in kilojoule per minute. I want this answer in maybe kilowatts, so I will multiply this value by mass of refrigerant. So this mass of refrigerant, now if you are using in whatever the unit you are putting over here, based on that you will get the unit. Suppose you are putting this particular MR in kg per minute, then you will get the heat rejected in kilojoule per minute. If you are putting this particular value of MR in kg per second, you get the heat rejected in kilowatt. So what I am doing, I am putting this value in kg per second. So let's say kg per second into kilojoule per kg. So kg get cancelled, you will get the kilojoule per second, which is nothing but the kilowatt. So I want to have the answer in kilowatt. So I am putting the mass flow rate of refrigerant in kg per second. Okay, that is 0.03, whatever the answer is given. And based on that, I get the heat rejected in the condenser is about 4.65 kilowatt. Okay, and then lastly the fifth formula, that is the fifth bit, rather, ideal COP. So ideal COP, we know that it is the minimum temperature. The formula is very simple: T min upon T max minus T min. Okay, so you have both the temperatures, T min, T max. So T min is nothing but the minus 25 degrees Celsius, that is the evaporator temperature, and the maximum temperature is nothing but the 40 degrees Celsius. However, you are supposed to take one care that you convert this particular temperature value of degree Celsius to degree Kelvin. Convert these values to degree Kelvin without fail, otherwise your answer will be wrong one. Okay, so convert these values to degree Kelvin. Minus 25 plus 273. You know the conversion, how to convert degree Celsius to Kelvin. So 40 plus 273 minus 25 plus 273. Okay, based on this you will get the ideal COP, and the ideal COP is about 3.82. Is about 3.82. Fine. So this is how you will be solving the problem. So don't get confused if the cooling capacity is not given. Read the statement very carefully and see that the per tier most they will mention. So per tier is nothing but for one tier. So this problem again was asked in the examinations many of the times. So this is what you are go about this particular problem. Fine. Thank you.